Good morning, ladies and gentlemen. This is Mark Lyons from GGI International in Hong Kong. We are a sister company of Golden Grain from Zhengzhou. So what I would like to do this morning is introduce to you some of our new items of equipment that we have been working on this past year. So I'm going to cover flow balancers, automatic moisture controller, and PU PLANSIFTER SIEVES. So first of all, just looking at our latest generation flow balancer, we refer to this machine as the DPMX. For those of you that are not familiar with what this flow balancer does, it's like a scale. It's measuring wheat from a silo, and it's mixing that with other wheats to go into the wheat cleaning plant or to the B1 roller mill. Now, in the lead up to improving our existing machine and developing a newer machine, of course, we studied what was available on the market, and we came up with a focus, if you like, in terms of what we wanted to achieve. Of course, accuracy. We want to have a machine that's better accuracy than what's available on the current market. We also want a machine that's low cost, competitive price. We want a machine that has low maintenance and long service life. So this was our focus, if you like. Now, in order to get to that focus, first of all, we looked at the principle of operation. This diagram here looks a bit complex, but actually it's pretty simple. We're just really explaining here what actually happens in a flow balancer. So the wheat comes in, it falls onto a measuring plate. The measuring plate is connected to a load cell. The load cell is connected to a controller, which gives the weight display. And of course, there's a gate here that can regulate the flow of wheat. So what we learned in our studies was that this height of fall from the inlet onto the plate is of critical importance, as is the shape of the plate, as is the angle of the plate. So these are the things that we determined during our research. Of course, we looked at the existing machines, the flow, how the wheat flowed into the machines, down the guide plate, onto the measuring plate. The measuring plate, of course, is connected to the load cell. And we studied and analyzed and tried to come up with something better. We looked at existing models that were in the market already. This is a model, I'm just going to call it Model 1 rather than identifying the actual milling engineer. This is the inlet, this is the gate, and this is the measuring plate. And this is the measuring plate is connected with the load cell. So the force of the wheat that's acting on the measuring plate gives a weight. However, what we found with this model is that the height of fall from the inlet to the plate was too large, resulting in an inconsistent accuracy. We looked at another machine that's on the market. Again, the wheat comes in, falls onto the measuring plate, which is connected to the load cell. In this example, we concluded that the angle of this measurement plate was too steep. So again, consistency of accuracy, not particularly good. This is another model that we studied. Accuracy a lot better, but quite a complex design, a lot of components inside. More components that you have inside a machine, there's more potential for failure to happen of one or two of those individual parts. Another thing that we noticed during our studies was the accuracy. The accuracy of the existing flow balancers on the market when they operated at low capacity was not that great. It's only when the capacity was a little larger, 3 to 15 or 6 to 30, that the accuracy became within accepted limits. So in developing a new machine, we wanted to address the accuracy at this low range, because not only are there small mills that want to buy flow balancers, but there's also some large mills that may want to feed back maybe broken wheat or small kerneled wheat into their main wheat stream, and they want to do that accurately. So for that reason, we wanted to address the accuracy at the low end. As mentioned, yeah, you have some of these models on the market. There's a lot of parts. Some of these parts are quite complex and quite expensive. So an average flour mill would need to carry these parts in their spare parts storage. So we came up with a new flow balancer machine that we called the DPMX15 and the DPMX30. 15 means 30 tons, 15 means 15 tons an hour, and 30 means 30 tons an hour. So not to state the obvious, but when you are ordering a flow balancer, make sure that you tell us your minimum range that you're planning to run it at and your maximum range, and then we can size the machine for you accordingly. This is the final configuration that we came up for the inside of our flow balancer machine. We have wheat coming in, we have gate. The wheat folds down a guide chute onto a guide plate, which comes into a measurement plate. This guide chute and measurement plate is connected to the load cell, which is linked with a controller, which can give us a weight display, or it can control the opening of a gate to give a certain feed rate that's desired. So with this design, we have achieved a very high precision. The opening and closing of the feed gate is achieved by an electro actuator. It's off the shelf, available from Siemens. Again, this means that as a flour miller, you can buy this directly from the manufacturer, or you can buy it from us. And that's one thing I want to emphasize. In a lot of our machines, generally, we try to use standardized parts that are available from various international suppliers, rather than customized parts. If we use customized parts, they can be very expensive, especially as time goes by and those parts, some of them become obsolete. So to make availability of some of these customized parts, you have to make a minimum order. And that long-term basis, that can get very expensive. This is the footprint of the machine, which you can study in due course. This is our test rig in the factory. Not that complicated, but nevertheless, it's a very useful tool that we can use not only to develop our new machine, the optimum configuration, but also to test our flow balancers before we send them out to our customers. So we can test for the accuracy and test for the consistent operation. Wheat comes in, very simple, flows through the wheat balancer, then wheat comes out and circulated. So very simple, but a very effective tool. Accuracy-wise, well, at the low end of the capacity scale, 2 tons per hour, yeah, you can see, and this is just a one-off reading, we've achieved 0.85. At 15 tons an hour, I have to put on my old man glasses here, we have achieved 0.38, and at 30 tons per hour, we've achieved 0.94. So very consistent accuracy. Can see here, these are pictures of the wheat flowing down the measurement plate, which is connected to the load cell. And this is the finished machine. We have a Siemens touch screen pad, which of course can be linked by Profibus to the central PLC unit. So any display that you have on this screen, of course, you can see it within your PC monitor within your control room. You can see here there's a perspex window, so the operator can see inside. And also, this is where the electro servo motor is housed. So it's a very compact design. These are some finished products in our factory. Some more finished products. I think this year we've sold something like, this year alone, we've sold something like 600 of these units. Some big flour mills being made in China these days, and also in the international market. Okay, I'm now going to talk about our latest generation automatic moisture controller. I think this machine should be familiar to you all, similar to the MIFA, if you like. It is a machine that's utilized to add water automatically onto wheat for conditioning purposes. There's basically two structures, if you like, for this machine. There's this tower-like structure, which we refer to the SFJC, and then there's the water panel structure, where the PLC unit is, and also the flow meter. Of course, flow meter sends water to the wheat mixer. Within the tower-like structure, we are measuring the moisture. We're also measuring temperature, and we're also measuring the wheat flow rate. And that information is being sent to this PLC unit, which is then comparing the dry moisture with the targeted moisture, and then it's automatically adding the water according to the target that's desired. The heart of the operation, which is located inside the tower-like structure, is this sensor. This sensor is the sensor that measures the dry wheat moisture and the temperature. It uses microwave energy and special software then to convert that microwave energy into a dry moisture and a temperature. Now, inside this tower-like structure is a flow balancer, very similar to a flow balancer, where we have the guide chute and the measurement plate together with the measurement arc. So this tower is measuring the dry moisture, the temperature, within this measuring box, because a certain proportion of the wheat will move down through this measuring box. And the larger proportion then will bypass the measuring box. It will fall on the guide chute and then onto the measurement plate, which is connected to the load cell. So the information from here is being sent to the PLC unit in the second section. The PLC unit then is processing the water requirement that's required to bring the wheat to the desired moisture target. Pretty standard flow of operation here. Basically, we have a filter, pressure gauge, solenoid valve. We have a water metering valve, and we have a water meter detection valve, a flow meter, and then water goes directly into the mixer. This is the footprint. Again, accuracy-wise, yeah, we're looking at between 0.1 and 0.3% accuracy. So let us say this is the international standard. Typically, we would guarantee 0.25%. These are some of the screens, some of the displays that we have available to us. These are the parameters. These are factory set and fine-tuned then during commissioning. Different mills do different things. Some mills, they tend to temper one wheat at one time. Other mills tend to temper a grist of wheats at the same time. So different mills do different things. And in order to give that flexibility, then we have these recipe pages, which can optimize the accuracy of this machine. Again, typically we have graphs that graph the water flow, the targeted against the actual. We have alarms. Again, all this can be linked by Profibus to your PLC with a display on your PC computer monitor within your control room. And this is the typical display. So we basically have the flow rate, the capacity, 24.97 tons an hour. We have the moisture. This is Ukrainian wheat. Moisture, this is dry moisture, 12.63. We have the temperature of the wheat, in this case, is 13.45. We have the density, we have the hardness. So these parameters affect the target water that's required to reach, in this case, 15%, which is our target moisture. So we have the targeted flow and we have the actual flow. These are some of our finished machines in our factory. This is an installation in Indonesia, and this is in the Philippines. I'm now going to talk about PU food grade PLANSIFTER SIEVES. Actually, these are are not that new. We've had these available for some years, but in the recent 1 year, we've had more and more inquiries because of HACCPs and a lot of flour mills. They do not want to use wooden sieves anymore, so they want to change to PU sieves. Now, some people call these plastic frames. Plastic is not technically correct, actually, but of course, if you ask us for plastic frames, then okay, we know what you're talking about. But basically, it's a polyethylene food grade material that we use. Some people call it PP, some people refer to it as PU. And this is the sieve. So these are the sieves that are inside your PLANSIFTER. Now you'll notice for the sieve structure, we basically have an outer sieve, which is the white part, and we have an inner sieve, which is this aluminium part. Now, in years gone by, this inner sieve or insert frame used to be wood. But in recent years, we have standardized this inner frame to become aluminium. And we have also, you will notice, standardized it to have a dimension that's the same as the outer frame. That's to say, the inner frame and the outer frame have the same outside dimension, which means that the available sieving area is a little bit more than the traditional sieve. The traditional sieve here tends to be the left, although in years gone by, this insert frame was wood. And then some milling suppliers have changed this insert frame to aluminium. This design here on the left, it has some problems in the sense that the wooden material, it tends to change shape over time, and you tend to get a gap between the inner frame and the outer frame. And that can allow coarse semolina to leak into the flour. And so to improve that, we developed this inner frame that, like I mentioned, is the same dimensions as the outer frame. So this picture here shows a wooden outer frame, but now we can change this wooden outer frame to a PU material. Some pictures here of this outer frame, stainless steel tray, which is riveted into position. More pictures here, side view, front view, and of course the aluminium inner frame fits here on top. Now, talking about this aluminium frame, you can see here how it looks like. This frame is made from a mold. It's not welded. These are not single pieces that are welded. It's made from a mold. So it's cast in a mold, it's taken out of the mold, it's sandblasted and polished. Underneath this part here, you will notice that there's a groove. And the reason for the groove is that it can fit onto a rail or a track. This rail or track is embedded in the outer frame. And what that does is that it prevents the inner frame from moving. Because sometimes, as you know, even though the PLANSIFTER section is compressed, after some use, it can become a little bit loose. It can lose a little bit tension. So in order to ensure that there's no slippage of this inner frame, as a safety precaution, if you like, we have this sieve, this inner frame with the groove and a rail to prevent any movement. So it locks us in position. The structure of the PU outer frame is a tongue and groove. It's a tongue and groove joint. So basically what we're doing is we're cutting the material to suit. We have experimented with a mold, a single piece mold, but the results have not been particularly good. We found that during the cooling process, it's very easy to get a deformation of the sieve. So it's very hard to get a consistent finish. And also the mold is very, very expensive, the single piece mold for the outer frame. And because of that, in the past, the price for these PU sieves has been quite expensive, maybe 30%, even more, higher than wooden sieves. But for our sieves, yeah, we can supply at the same price as wooden. So we've come up with a very pragmatic, cost-effective solution, if you like. This is the finished frame. You can see here, aluminium frame with the mesh. We can use SIEVES or SATI mesh. The customer can let us know. We don't mind, price-wise, it doesn't really make too much difference. You can see here the cleaners. Some more pictures here of the aluminium frame, which is on top of the rail. These are the sizes that we have available. GGI or Golden Grain, we have two sizes that we tend to standardize, 640 and 740. Because the inner frame is the same dimension as the outer frame, we get a slight advantage in the net area, in that it's a little bit more than the traditional frames. 640 is the same as MPAG, so that's what we can do. Also, we can also do MPAH. We can do GBS, Sataki, OMAS. So these are the standard frame sizes that we have. The one frame size that we don't have actually is the Okram, because Okram is 750, 750. We have had some inquiries if we can supply. And if you are an Okram mill, please send me your inquiries. We will consider, because obviously the mold cost is very, very expensive. It's a big investment, and so, you know, the only way we can justify it is by basically getting some orders, and that's how we get the payback. So any Okram mills out there, yeah, do send me your inquiries, and we will consider it. Typically, if a flour mill wants to give us an inquiry for a PLANSIFTER replacement section, yeah, they will send us these drawings. These drawings are in your master technical files. Different milling engineers have a different style, but it doesn't matter, we can follow. Then we can manufacture according to your existing arrangement, and then we can deliver in this format. So you can take out your existing PLANSIFTER section and you can slot in this new section. So it's a bit like a plug and play. It can be done in a matter of half an hour or so. Thank you very much. If you have any questions, please contact me at info@g-grain-intl.com. That's info@g-grain-intl.com. Thank you very much. I hope this next time we meet, next year, I hope we can meet face to face. Thank you. Bye-bye.